Hello everybody, welcome back to the YouTube channel of the Biochem group. Today we're going to talk about some redox properties of nucleobases that compose the DNA and how to compute these properties using both static and dynamic approaches. But first, let me motivate you a little bit with an example. The reason why it is of paramount importance to know accurately the value of these properties in nucleobases. Nowadays, the presence of many analytes is determined qualitatively or quantitatively by means of a biosensor, which it is a type of sensor whose receptor is a biomolecule. Today, we are going to focus on DNA-based biosensors, in which an ensemble of single or double-stranded DNA is anchored to a metallic surface. That way, the DNA is able to perform a redox reaction with the target analyte. Usually, the receptive region of the DNA is oxidized and this whole is transferred along the full strand until it is held in a metallic substrate. Thus, this kind of sensing involves charge transfer processes. Typically, the nucleobase is the main moiety that participates in these charge transfer processes, and therefore the redox properties of these residues must be known. As a result, many experiments and theoretical calculations have been carried out in order to accurately determine these values for each of the nucleobases. Let me now define the term one-electron oxidation potential. It is a redox property which it is the potential of the oxidation process but considered in the direction of the reduction. So, a clear value for the one-electron oxidation potentials of nucleobases cannot be extracted from the literature due to the large variety of results. The aim of this work is to establish a standard protocol that let us compute such these properties with the highest accuracy possible. As I have said, several protocols were tested, including static and dynamic approaches. Firstly, two different static protocols were compared: a direct determination of this property and a determination using a thermodynamic cycle. In both situations, a continuous solvation model was used in order to describe the solvent. The first idea that came into our minds was to simply calculate the free energy of both the neutral and the cationic species of the considered nucleobase, and apply a direct determination of the free energy of reaction, as this equation shows. However, the static direct recipe can lead to some errors, taking into account that we are assuming that the nucleobases are in water at 300 Kelvin. For instance, the parameterization of the solvent already accounts for thermal effects, so they are double counted. And the ideal gas partition functions cannot be applied to compute thermal effects for solvated nucleobases. Alternatively, the free energy of the reaction can be also computed using this thermodynamic cycle, in which we first desolvate the cationic species, then we perform the direct determination in gas phase, and then we solvate again the neutral species. All these terms are included in this equation that we can see. Two different versions of this thermodynamic cycle were tested. In the first one, the geometric relaxation of the solute upon solvation was considered, whereas in the second version, this relaxation was not taken into account. The use of all these equations and the introduction of the standard hydrogen electrode as a reference electrode lead to the computation of this property within the static direct approach and the static cycles 1 and 2 approximations. It is important to highlight that this term is just a correction to balance the potential of the semi-reaction of the standard hydrogen electrode, in which the electron is also taken into account. The plot presented here shows the signed errors with respect to the one-electron oxidation potential reference for each nucleobase, computed with PBEOP, MO62X, and B3LIB functionals within the static direct framework. These values represent the mean unsigned error for each of the functionals. When presenting this plot for each of the static schemes, it is possible to observe the following facts. In general terms, B3LIB and MO62X overestimate the potentials for almost all nucleobases. Despite this, the accuracy of the functional is system dependent. For example, the potential of adenine is better described with B3 lip. On the other hand, the potential of guanine is more accurate when it is computed using MO6-2X. And in the cases of the pyrimidine nucleobases, PBEOP is the most appropriate functional. In terms of the protocol employed, the static cycle 2 scheme provides slightly higher mean unsigned errors values than the static cycle 1, giving evidence that the relaxation upon solvation is not relevant in these systems. In addition, the static direct scheme is the one that provides the closest values with respect to the reference for the three functionals, and this means that the inaccuracies of the approach are not important or there exists error cancellation. Specifically, the determination is very accurate when using PBEOP functional. Next, conformational motion was introduced in the theoretical model through molecular dynamic simulations. Sampling was included because many systems do not present a single clear global minimum in their potential energy surface, but many local minima which are thermally accessible. In these situations, there is a need to explore different conformations along the relevant regions of the potential energy surface. Let's take the initial definition of the reduction free energy. Free energy of each species can be averaged from the ensemble of configurations obtained through classical molecular dynamic simulations. This methodology, named dynamic direct approach, also employs the adiabatic ionization energy as all the static methodologies. Similar plots as presented before are shown in this slide. On the left side, errors from the static direct approach are plotted, whereas on the right side, they are described for the dynamic direct approach. It is possible to see that the mean unsigned errors for both methodologies are pretty similar. The nucleobase that presents the most important variation in its potential is cytosine, but in general terms, there is almost no variation on these properties from one scheme to another. In view of all these observations, it can be stated that sampling effects are not relevant in this situation. After this, the Solvation model was studied for the dynamic protocols. Concretely, two different Solvation models were tested, an implicit one using COSMO and an explicit one using TIP-3P force field. When using the implicit Solvation model, the solvent is defined by a dielectric constant and atomic radii, characteristic of each solvent. On the other hand, the explicit solvent is described by electrostatic atomic charges. As a result, the implicit solvation model represents a polarizable embedding in which both the solute and the solvent polarize mutually. On the other hand, in the case of the explicit solvation model, it represents an electrostatic embedding example in which only the solvent polarizes the solute. The goal of this study was to check whether the solvent model could affect to the value of the molecular properties. Showing the signed errors in both methodologies, dynamic direct implicit and explicit, these are clearly lower in the case of COSMO in all the cases. Therefore, the one-electron oxidation potentials obtained with the implicit solvent model are more accurate than those obtained with the explicit one. This fact indicates that polarization effects are more relevant than specific interactions in these systems. Then we also tested an alternative formulation called Marcus theory, and we compared it to the dynamic direct approach. The application of the Marcus theory could be brought to provide more accurate results than the direct protocol due to the greater complexity of the Marcus formulation. Leaving apart the direct equation, which directly computes the adiabatic ionization energy of the oxidation process, there is an alternative formulation, as I said, Marcus theory, that is able to compute these redox properties through this equation. In this case, the formulation uses the average between the vertical ionization energy and the vertical attachment energy of a Hall redox equation. But first, the viability of using Markov's theory must be checked, since it is an approximation obtained from several hypotheses. This first plot, obtained from the direct Markov's implicit protocol from adenine, represents the energy distributions of the vertical ionization energy and the vertical attachment energy centered in the expectation value of the correspondent energetic term. In order to check if the system follows a Markov regime, the distributions of vertical ionization energy and vertical attachment energy must have the shape of Gaussian functions. In addition, the standard deviations of both average values must be equal one another. So, for the case in which COSMO is applied, the system follows this Markov regime, and so Markov's theory can be successfully performed. Again, this test can be expanded to the explicit solvent model. In this case, the distributions are far from being Gaussian functions with respect to the implicit model. In addition, standard deviations are not equal. Consequently, when an explicit solvent is used, the Markov theory does not work properly, contrary to the case for which COSMO is applied. However, there exists a correction described in this equation that can be implemented to the Markov calculation of the one-electron oxidation potential to balance the lack of linear response of the solvent. This equation accounts for the different reorganization energies defined by these three expressions below. When the Markov theory is checked and corrected, we will proceed to observe the differences between the dynamic direct determination and the dynamic Markov theory. We will start comparing the case in which we use implicit solvation model. Results show that the mean unsigned errors for the dynamic direct implicit approach are similar to the mean unsigned errors obtained from the dynamic Markov implicit protocol. Consequently, there is not an improvement in the results when implementing Markov's theory with implicit solvent. Now, let's check the case in which we use explicit solvation model to describe the solvent. In this case, the dynamic Markov approach agrees better with experiment than the dynamic direct approach for the PBOP and P3lib functionals. And surprisingly, the opposite is true for the MO6-2X functional. As a result, Markov's theory improves significantly the one-electron oxidation potential of nucleobases when performed with explicit solvent. If we also compare the solvation model in the framework of the Markov theory, conclusions extracted from the dynamic Markov protocols are similar to the ones discussed for the dynamic direct approaches. The implicit COSMO solvation model provides results in better agreement than explicit TIP3P due to the reorganization of the charge distribution onto the cavity of this last one. Thus, polarization effects are again more relevant than specific interactions. So now the question is, what is the difference of applying either the implicit or explicit solvent model? So let's briefly explain the procedure to obtain the one-electron oxidation potential using the dynamic Markov implicit protocol. For the calculations of the vertical ionization energy and the vertical attachment energy, classical molecular dynamic simulations are run for the neutral and the cationic species respectively. Taking a large number of snapshots of the neutral trajectory, we can compute the electronic energy of each of the snapshots. If we average all these energies, we are somehow taking into account the thermal effects of the system, and we can say that we are computing the free energy of the neutral species. Analogously, if we take the cationic trajectory, we could do the same with the cationic species. For the neutral trajectory, the same geometries employed to obtain the free energy of the neutral nucleobase are used to compute the electronic energy of the cationic species without relaxation, and the average of all these energies give the free energy of the cationic species. An equivalent procedure is carried out for the cationic trajectory to compute the free energy of the unrelaxed neutral species. Thus, The difference in energy between the cationic and the neutral species within the neutral trajectory gives the average value of the vertical ionization energy. And the vertical attachment energy is obtained similarly within the cationic trajectory. Finally, the oxidation-free energy is computed as the average of the vertical ionization energy and the vertical attachment energy. Same procedure is applied to the dynamic Marcus explicit approximation. As it can be observed, the unrelaxed geometries are higher in energy than the relaxed one as expected. As a consequence, the vertical ionization energy is always higher than the vertical attachment energy. However, the energy gap between the relaxed and the unrelaxed species within the same protocol is significantly higher in the case of the explicit solvent, leading to a higher vertical ionization energy and a lower vertical attachment energy with respect to the situation in which COSMO is employed. This can be rationalized as follows. When the vertical ionization energy is computed by removing an electron from the snapshots of the neutral trajectory, in the COSMO solvent model, the tesseract charges of the cavity change to adapt to the positive charge of the solute because of the existing mutual polarization between solute and solvent. Therefore, the reorganization of the solvent charges is stabilizing the unrelaxed geometry of the cationic nucleobase. As a result, the energy difference between the unrelaxed and the relaxed cationic solute is not too large. However, in the electrostatic embedding QMM calculations with explicit solvent, the charges of the solvent do not relax upon ionization of the neutral trajectory, because TIP3P is a fixed charge force field. Therefore, the energy of the unrelaxed cationic nucleobase is much higher than the energy of the relaxed one. The same explanation holds for the vertical attachment energy computation. When the cationic trajectory is neutralized, the unrelaxed neutral geometry is much more stabilized in COSMO than in TIP3P. Surprisingly, despite the dissimilar behavior between the unrelaxed trajectories for COSMO and TIP3P, the results obtained by the dynamic Marcus protocol in both solvent models are not too different, because TIP3P overestimates the vertical ionization energies but underestimates the vertical attachment energies, making the average of both magnitudes similar to the one computed with COSMO. However, the slightly better performance of the COSMO calculations is likely explained by the polarizable nature of the solvent model. In conclusion, within the static approaches that have been tested, the static direct approximation provided the most accurate results. The relaxation of the geometry from gas phase to aqueous phase does not play an important role in this kind of systems. As seen before, the best static and dynamic schemes provide similar results, leading to the statement that sampling effects are not important. Since polarizable effects dominate against specific interactions in these systems, a polarizable embedding like COSMO is more appropriate than a solvent model that represents an electrostatic embedding. The introduction of Marcus theory improves the accuracy of the results concretely in the explicit solvation model case. Over the functional that have been tested, PBEOP is the best one for the computation of the redox properties of nucleobases. Thus, if we put all this information together, the best choices are the use of PBEOP, COSMO, and Marcus theory in the case of dynamic approaches. So the best protocols are the following. The first one is the static direct approximation due to the low computational cost and the irrelevant role of the sampling. Secondly, the dynamic direct implicit scheme, although the computational cost increases a little bit. Finally, the dynamic Marcus implicit framework, although again it is more computationally demanding than the dynamic implicit scheme. However, it is possible to obtain lower standard deviations to give a more accurate result. So finally, I want to thank the whole MoBioChem group, the FPU grant, the CCC Computational Center, and also Professor Sergio Díaz Tendero for all the help given. So thank you very much for paying attention and attending to this talk.